Right, here we're looking at section 4.1, and you really just need to ignore this for right now. We're working on it. So our essential question for this section is we're really just starting this new chapter, and we're going to be dealing with polynomial functions, okay? So our big question is, what are some common characteristics of the graphs of cubic and quartic polynomial functions? So we've looked at several polynomials before. We've looked at lines and we've looked at quadratics. Now we're just going to add a couple more. So here we're going to add in some cubic and some quartic. So where our exponent is 3 and where our exponent is 4. And we'll continue looking at some more of these. So here's our learning targets for today. First, we're going to identify polynomial functions. Then we're going to graph them using tables and end behavior, and we'll talk a lot about what end behavior means. So first, a polynomial function looks something like this, right? And like I said, we've been dealing with some polynomial functions before. We've looked at linear functions, we've looked at quadratics. So remember that a monomial is a number, a variable, or the product of a number and one or more variables with whole number exponents. That's the big key, whole number exponents, okay? So just some terms we have. So our first term is a leading coefficient. The leading coefficient is the number in front of the term with the highest exponent. The degree is that highest exponent. And then our constant term is our term with no exponents. Okay, so when we are writing this in standard form, we always start with the highest exponent and then work our way down. So now let's look at a couple of these. Okay, so we have to determine if these are polynomial functions. So let's look at A. So first thing I notice is I have all of my exponents are whole numbers. So I'd say, yep, that's a polynomial. And then I have to write it in standard form. So I have to go from biggest to smallest exponent, which it's already done. So that's already written in standard form for me. Okay, so I can see the type of function. The type of function just tells me kind of what the degree is. So this would be a cubic, since my highest exponent is a 3. The leading coefficient here would be this -2, because that's the number that's with the highest exponent. Let's look at here at B. So first I have to determine, is this a polynomial? I see all of my exponents are whole numbers, so yep. So to rewrite this in standard form, I have to take the highest variable first, so 2x to the 4th minus 0.8x cubed minus 12. So now my exponents are decreasing in order. So this, with a 4, right, we've talked cubic, this would be a quartic function, okay? And then our leading coefficient right here is that square root of 2. It's the value that is with the highest exponent. So let's look at C. The first thing I notice about C is I have this negative exponent. Whenever I have a negative exponent, that is not a polynomial function. Okay. Ooh, and in your book, you'll see that this looks a little differently. This is actually x squared plus 3 to the x power. Okay. So again, I see my exponent here is not a whole number. It's a variable, so that is not a polynomial function. So look at these and see what you think. And if they are polynomials, how can you write them in standard form? So now we're going to evaluate these polynomial functions. Whenever you see evaluate, that's where you take the number that they give you and plug it in everywhere that you see an x, or the variable in the function. So let's just plug that in. So I've got 2. I'm evaluating when x equals 3. So I've got 3 to the 4th minus 8. And then there's an x, so 3 squared plus 5 times my x is 3 minus 7. One thing you'll notice that I will always do is whenever I'm evaluating or substituting anything in, you always want to use parentheses. It'll make it a lot cleaner, and so you won't lose things as much. So now let's start evaluating. So I still have this 2 times 3 times 3 is 9, times 3 is 27, times 3 is 81, minus 8 times this 3 squared is 9, plus 5 times 3 is 15, minus 7. I just always want to do these one step at a time. So now I can multiply 2 times 81, which is going to give me 162, minus this 8 times 9 is 72, plus 15, minus 7. Well, so now I see 162 minus 72 would give me 90, plus 15, minus 7. 90 plus 15 is 105 minus 7. And 105 minus 7 would give me 98. So now that I've completely evaluated it, this is my final answer. When x equals 3, my function f of x equals 98. So now we're going to talk some end behavior. Okay, so end behavior is what we look at as x approaches positive infinity and x as approaches negative infinity. So we will know with our polynomial functions, our domain is always going to be all real numbers. So we want to know, what does it look like as we get super huge in the x and super small in the x? And there's a pattern that we can follow. So these top two are if my degree is odd. And remember, the degree is that highest exponent. So if my degree is odd, I know that one side will be up and one side will be down. So my leading coefficient, right, that number that's in front of that variable with the highest exponent, if that's positive, I will go towards the positive as I go positive. If it's negative, as I read from left to right, I will go negative. Okay, so that's what these are saying. And how we read this mathematically is f of x approaches positive infinity as x approaches a positive infinity. That's just kind of how you read these little statements. So now what if the degree is even? So if the degree is odd, I see one is up and one is down. So if my degree is even, they're either both up or both down. And I can tell by if my leading coefficient is positive or negative. So if my leading coefficient is positive, they'll both be up. And if my leading coefficient is negative, they'll both be down. So that's just going to help us as we start graphing these polynomial functions. Okay. So here I want to describe the end behavior of this graph. So the first thing I see is it's already written in standard form, so I don't need to do that, because that's always the first thing you're going to want to do. So I see first that my degree is even. So I know that it's going to go either both up or both down. And so then I have to look at this leading coefficient, and since it's negative, I know that both are going to go down. So it'll look something like this. And then I graph it, and I just see, yep, I was pretty close. Both as I approach negative infinity and as I approach positive infinity will reach infinity, negative infinity, right? So we always want to just see, is this even or odd? And then is it going to go up or down? That's really the questions we kind of ask when we're looking at these polynomials. So now I want you to try these. Definitely look down at this number 6 and see if you can see what the end behavior would look like for that one. So now here's a couple we're going to graph and look at. So when we're graphing these polynomial functions at this point, we really just want to plot some points and then connect them. So the first thing we do is we make a table of values, and then we plot them, and then we plug those in. So anywhere I'd see this, see an x, I'd plug in a -2 to come up with my f of x. Again, I'd plug in a -1, 0, 1, and 2. And generally these are pretty good numbers to use. They're generally pretty simple. So then I can connect them. And I always want to just double check my end behavior. So for this one, I see that it's odd, so one will be up and one will be down. And my leading coefficient is negative, so as I lead from left to right, it will be going down. So I start up and I go through my points and I end down. So here on part B, I'm going to look at end behavior first. So I see that I'm even, so they're either both going to be up or both be down, and this leading coefficient is positive, so I know they're both going to be up. Okay, so then again, I just plug in some points, I come up with some x values, and again, you'll see I picked the same x values, and I plug them into my function, and I come up with my f of x values or my y values, and then I plot those points, and I connect them using my end behavior with a smooth curve and see exactly what it looks like. Okay, so here I'm given some characteristics of this graph, and I have to sketch what the graph looks like. Okay, so here's what we can kind of look at. So if f is increasing when x is less than 0 and when x is greater than 4. Okay, so I like to draw myself a little hint here. So I see when f is less than 4, less than 0, it's going to be increasing, and we're going to say that that is 4. It's also going to be increasing on this side. So it's decreasing between these two, between my 0 and 4. So here it's going to be decreasing. Okay, so f of x is greater than 0 when between -2 and +3. So I know it's going to be above the x-axis, and when it's greater than 5. And then I see it's going to be less than 0, so underneath my x-axis when x is less than -2, and here in between these two things. Okay, so And then I can use this graph to help me figure out what the degree is. Well, first I can see that I'm going to end going up and end going up. So I know that it's going to be an even exponent. Then I can just take a chance and kind of graph what I was looking at. And so here's exactly what we were looking at, right? So I'm increasing here. Oh, and I just drew my arrow wrong. I was incorrect here. This is going to be odd. This is why I need to be very careful when I draw my arrows, because up here I drew it going this way, but in reality it's still increasing this way as I read from left to right. Okay, so you'll see we're increasing and then decreasing and increasing again. Here between my 3 and my 5, I am below the x-axis, and here when I'm less than -2, I'm below my x-axis. Now this is just one kind of guess of what this graph could look like. It could go super high in between here and super low, but we were not asked that. We were just asked kind of the shape of this graph. So we can simplify things a little bit that way too. Okay, so now here's some of our word problems, and we're going to be dealing with word problems a lot with polynomial functions. So the estimated number V, we're calling this V, which is in thousands of electric vehicles in the United States, can be modeled by this polynomial function, right? Big one. So T represents the year, where T of 1 is 2001. So if T was 0, it would be 2000. Okay, so I want to use a graphing calculator or Desmos to graph the function between 1 and 10. So I only care about 2001 to 2010, and then I want to look at the behavior of that graph. Okay, so then I want to find the average rate of change from 2001 to 2010, so in this same interval. And then I want to kind of figure out, can I use this model for stuff for cars before that or for cars after that, and kind of explain what I'm doing. So I go ahead and I graph it, and here we just used a graphing calculator. You can use Desmos, it doesn't matter. But just remember to limit your values, right? We only cared from X or T from 1 to 10. Okay, so I see that my electric cars increased pretty greatly at first, but then right around 2005 kind of leveled off and are still slightly increasing. Okay, so that's how we can just graph our little, just a piece of our function and kind of talk about what it means for the context of the problem. So when I'm finding the average rate of change, I have to find this point right here and this point right here, the X and the Y. So here I'm given the X's, right? It's going to be 1 and 10. And then I can just use my graph. And remember, on Desmos, you can click on these points and just find exactly where you want to be and find my average rate of change. So I take my V or my Y, so my change in Y over my change in X gives me an average rate of change for that. So it tells me, in the context of this problem, that about 4.4 thousand electric vehicles per year, there was an increase of approximately 4.4 thousand vehicles per year. That's what the average rate just tells me. And then C, I want to talk about, can I use this model continuing forward? Well, and I kind of can. So since my degree is odd, right, and we can see that up here, the degree was odd, but this is positive. That means my end behavior as I go further and further to right will continue to go towards infinity. So since that is the case, I say that I could have unlimited growth. As T continues to increase, I could have this just crazy unlimited growth. However, we don't think that that's a very reasonable answer, right? Because we're starting to kind of level out. Yeah, we may hit this huge jump again, but we always want to think about the technology. So electric cars will not always be on an increase just because of new technology and things like that. Then we want to look down here as well. At this point, we can see that it's going very negative, and we know we can't have negative electric cars, so I don't want to use this model for anything prior to this because I don't think it would be very accurate of an estimation. So now here's some that I want you to graph. And remember, at this point when we're graphing them, we're going to just be looking at plotting some points, so picking some X values and looking at end behavior of each graph and then drawing a curve through those points that you've picked. Okay. So now really look at this one. See if you can kind of figure out what your graph is looking like between these different points and see if you can give a general sketch. And then our last little piece that we want to think about is if we have a different model which here we can see it now. If we have this model instead of the model that we just talked about for that last example, what would it look like? Would I still want to use that model? What's my average rate of change like? So let's look back at our learning targets. So first we identified polynomial functions. And remember that a polynomial function has to have a whole number exponent that's positive. Then we graph some polynomial functions using tables and end behavior. And this is just where we plot some points, we pick some x values and plot those, and then look at the end behavior based on if we've got an even or an odd degree, and then if a positive or negative leading coefficient. So now that we've worked on these learning targets, go ahead and work on your homework for 4.1.